begin. Our next speaker is Chahat Ahuja, who talks on visibility of lattice points across polynomials. Please.
Thank you. Thank you, sir, for the introduction. So, good morning, everyone. My name is Chahat Ahuja, and I'm from India. I have just completed my bachelor's in computer science and mathematics from Delhi, IIIT Delhi, India. And it is an honor for me to present my work here today. And this is the first time I'm presenting my work at such a huge scale. I would first like to thank the organizers for giving researchers like me from all across the world to showcase a platform to showcase our work. And today I will be presenting our work on titled Visibility of Lattice Points across Polynomials. So before we dive deep, I would briefly like to outline the structure of the talk. I will first start by defining the classical notion of lattice point visibility, which I will then extend to polynomial curves and present our main results. This will include a characterization of visibility and corresponding counting formulas. Following this, we will start with a construction that reverses the problem which we started with and present some computational results on the clustering of invisible points. I will then conclude with some directions for future research. Thank you. Let's begin. So we begin with the classical notion of lattice point visibility. An integer lattice point is said to be visible if a direct line of sight from an origin can be drawn to it. Formally, a point a comma b in integer square lattice is visible from the origin if there exists no lattice point from on the line segment joining the origin and a comma b. As it is the figure on the right, it illustrates this concept. If you can see, a comma b is obstructed by a point a dash comma b dash, whereas a dash dash comma b dash dash has no such obstruction. So a dash comma b dash and a double dash comma b double dash will be visible, and a comma b will not be visible. This leads to a key observation. A point a comma b fails to be visible if and only if there exists an obstruction point, that is, any point for which a dash comma b dash a dash is less than a. And it also satisfies the equation b by a is equals to b dash by a dash. That is, some closure point lies on the exact same line to the origin, thereby justifying the same slope. Now, from these results, we can draw two consequences. First, every non-visible point lies on a line that is already occupied by a closer visible point. And second, the set of visible lattice points is in one-to-one correspondence with the lines to the origin of the rational slope. This also includes the vertical line of infinite slope. Now, this brings us to another classical equivalence that any point is said to be visible from origin if and only if A and B are co-prime. This proof has two directions. Let us start with the first direction. If GCD of A comma B is prime, since A and B share no common factor, the fraction B by A is already in its lowest terms, and no smaller pair with A dash comma B dash with A dash less than A can reproduce the exact slope, making A comma B visible. Conversely, let us suppose A comma B is visible. So no closer point lies on the same line through the origin of this point. This absence of the closer point forces GCD A comma B to be 1. Otherwise, dividing the coordinates by their common factor will produce exactly such a closer point with the same slope, which is not the case. Together, these give a full equivalence, and this is the classical result which we will now generalize to polynomial curves. We move on to the next section where I define where I extend this notion of visibility from straight lines to polynomial curves. Let P of x be a polynomial with non-negative co-prime coefficients. The reason we chose co-prime coefficients so that the polynomial is already in its lowest terms and there is no further reduction required. Now we define visibility as follows. We say a point a comma b is P visible if there exists a positive rational Q such that B is equals to Q dot P of A and there is no other lattice point that lies on the curve y is equals to Q dot P of x between the origin and A comma B. In other words, A comma B is the first lattice point this curve actually is. And if we see closely, if we take P of x to be x, this definition perfectly collapses to the classical visibility which we just discussed. Now, every point on the curve shares some value of y divided by P of x. So, the ordinary slope, B by A, the natural quantity which we will talk about here is the transform slope, which is B divided by P of A. Visibility then becomes a statement about distinct transform slopes. So, A of B is only P visible if and only if there is no earlier point for which A dash comma B dash with A dash less than A shares the same transforms curve. We can turn this into something that is directly checkable. Since A comma B lies on the curve, any earlier point on the same curve must satisfy B dash equals to B divided by P of A into P of A dash. Such a point exists exactly when this quantity is a positive integer. So A comma B is P visible if and only if there exists no A dash which is less than A, for which B into P of A dash divided by PA is an integer. This again falls in the polynomial curve analog of GCD of A comma B is equals to 1. Naturally, just like we had a single divisibility test in the case of integer lattice, we would like to check the same case for the polynomial lattice as well. So now we define GCDP. GCDP is the largest number that is defining both P of A and B. Similarly, when if we put P of X to be X, this reduces to the classical definition of GCD. So the natural guess is of GCDP A comma B is equals to 1 should be equivalent to P visibility. Now, we examine whether this guess holds or not. So we first prove the forward implication. We start with the assumption that GCDP A comma B is equals to 1. And since A comma B lies on the curve with Q is equals to B by PA, we need to find any value of P which is less than A such that B by PA PT is an integer. Because P is increasing and PT is less than A, since P of A has non-negative, P of X has non-negative coefficient, so it makes it a monotonically increasing function. And since GCD P of A comma B is 1, there is no prime that divides both P and P of A. So the fraction PT by PA cannot reduce to a whole number. Hence, no lattice point exists between the origin and A comma B, making A comma B P's. However, when we come to the converse usually fails. We take a counter example where P of X is taken as to be X square, and we consider the point 2, 2. Now, to get the GCD P of 2, 2, the answer comes out to be 2. However, if checking the condition which says that for no A dash less than A, B PT by PA should not be an integer, does not follow. If we check for A dash equals to 1, B PT by PA perfectly comes out to be an integer, which is not true. So 2, 2 is genuinely P visible, even though GCD P is not equal to 1. So we are left with only single implication that GCD P guarantees visibility, but visibility does not guarantee GCD P is equals to 1. This gap is exactly what motivates our next construction. Now, I would like to next move to the next section where we introduce some more notations and terms to cover this gap. So, till now, we discussed that GCD is equals to 1, it guarantees visibility, but the converse can fail. So, our goal here is to find a single divisibility condition and which ultimately gives us some measure for the density or some counting number, which can give us a better idea of how visible lattice points are distributed in the polynomial lattice. Now, for that, we define LPA. For a fixed A and each t less than A dash, we define a quantity known as dt, which is PA divided by the GCD of PA and PT. Intuitively, if you look at it closely, PT is essentially the leftover part of A once its shared factor with PT is removed. How so? PA divided by, if we divide PA divided by the GCD of PA and comma PT, the leftover part is left. Then we define LP of A as the least common multiple of those dt values. How is this relevant is now how it's relevant to lattice point visibility, which that part we will see right now. So if B and LP are co-prime, so instead of P of A, we are now talking about LP of A. Then B dot PT by PA is never an integer for t less than A. Hence, A comma B is P visible. We will now show this by contradiction. So we start with by an assumption which says GCD B comma LP of A is equals to 1, but for some t, B PT by PA also equals to some integer. Now, since B PT by PA is an integer, we can say that B PA divides P. B dot PT, which forces dt to divide P. Now, from the definition, we saw that dt is nothing but the LCM, LP of A is nothing but the LCM of all the dt's that we calculate. And so dt will naturally be divide LP of A, and we just showed that dt also divides B. So dt will also divide the GCD of B, LP comma A, and it will the GCD of B comma LP comma A is equals to will be nothing but dt. We also show that dt since t is less than a, we also have that pt is less than a, and because the GCD of pt comma pa is less than pa, dt will always be 1. So putting these together, we know that GCD of b comma lpa can never be 1. Hence, getting us to a contradiction that there can exist no t for which p by pa will be an integer, guaranteeing visibility. Now, we also give one quick remark. We know that dt divides PA, which we just showed, and BDT also divides LP of A. So we can say that the primes that are dividing LP of A will also will be a subset of the primes that are dividing P of A. Now, we move from this criterion to a count. We use the principle of inclusion and exclusion to get a proper result on the number of visible points there are. So before that, I would like to state the inclusion principle. So stated generally for sets V1 through Vn, the count of elements avoiding all of them equals an alternating sum over subset J of the size of the intersections of sets indexed by J. In our setting, each BT is the set of B's up to N which are divisible by D, A, comma T, which we just discussed in the LP proof, and the intersection over the subset J is exactly the set of the multiples of the least common multiple of those D, A, comma T. So this gives us our counting theorem. The number of P visible pairs A, comma B with both coordinates up to N are given by this double sum. Summing over A for 1 to N, for each A, an inclusion-exclusion sum over subsets J of the earlier indices with terms involving the floor of N divided by the least common multiples of the corresponding D, A, comma T, which we just discussed in the LP proof. Now let's get to the proof of this. We start by fixing A, and by definition, we know that any value of B fails visibility at exactly when MAT divides B, which we also discussed in the LP of A proofs, that BPT by BA then does not turn out to be an integer, so guaranteed. So thus failing visibility. Now applying inclusion to these sets, the number of B's avoiding all of them is exactly this alternating sum, where each term counts multipliers of the relevant least common multiple using the convention that empty LCM is 1, so the empty subset contributes to N. The inner sum gives one for one fixed A, exactly the number of P visible P's, and summing this over all A from 1 to N yields the stated double sum, completing the proof. Now we move to the next problem. So far, we have only discussed, we fixed a polynomial Px, and we tried to find points which were visible. We now reverse the question and we check, given any lattice point P of A comma B, does there exist a polynomial for which the point is visible? In the classical case, visibility is fixed once for all GCD A comma B. But once we allow the polynomial curve, the curve itself to become something that we get to choose. So if A comma B isn't visible around the straight line, can we instead find a curve A comma B that avoids every earlier lattice point? This turns visibility from a fixed property into something that we can find. Our strategy will be to use the base A digit of any large prime N to build a polynomial whose coefficients are forced to make A comma B visible. So this is the formal theorem that we got. Given A comma B and the prime L, which is larger than both, we write L in base A and the digits A, AD through AN, which is the AB representation of L. We now define P of X using these digits, which is scaled by B and L. Thus, then A comma B lies exactly on this curve and there is no lattice point between the origin and A comma B. The proof is very short. Since L base A example is exactly the digit sum that is mentioned here, we can see plugging in A, X equals to A, make A's cancel and the digit sum collapses back to L, leaving PA equals to B. So the curve genuinely passes through the target point. Now, the next thing that we have to prove is that BPT by PA is an integer. So now we fix T between 0 to A. And since any digit is bounded by A minus 1, the digit sum strictly is less than N. And since L is prime, it does not share any factor with the sum. So L also exceeds B. So the factor L sitting in the denominator will never cancel and PT is never an integer for any T between 0 to A, which completes the proof. So for any target point, we can engineer a polynomial built from a large prime's expansion that makes it visible. But this construction, if we see, it's highly tailored. It depends on a specific prime and a base expansion. So it helps in proving existence, but it does not provide any helpful structure. Now, this motivates our next question, which we will discuss, that rather than engineering one polynomial per point, what does visibility look like across a nature of a family of polynomials, and how are invisible points scattered? That is where the Python simulations, the computational part comes in. We now move on to the last part of this talk, where our results so far describe global asymptotic behaviors. We saw formulas, densities, growth rates as n becomes large. However, now we will get to something different. A natural question that arises after seeing those results are whether invisible points scatter uniformly or not. Prior work on the classical case has already established real structure. Murphy classified n by m invisible blocks for n m up to 4 under the ordinary GCD condition and found that invisible points clustered into structured blocks rather than appearing randomly. Lystrom and Luca went further. They tried to study minimal rectangular patches of non-visible points and gave explicit bounds to the same. So motivated by this, we took up one family, that is f of x equals to ax squared plus bx. And of course, we took both of them to be co-prime and we started looking for 2 cross 2 blocks of invisible points. This is just recalling the definition of p visibility here, that a comma b is p visible if b pa dash by pa does not belong to any set. The algorithm that we searched, we designed has 4 points. The first function is the polynomial evaluator, which running in linear time and degree, which helps in computing p of t, p of a, p of a dash. Second, the visibility checker. The visibility checker codes the bpa dash divided by pa for z. It takes inputs as b and a dash, and for all a dash less than a, it checks whether the point is visible or not. Third, we will introduce a breadth first search starting from a point which expands outward to find the nearest visible neighbor. And fourth, the region scanner that sweeps a bounded grid. It takes the maximum and the minimum as input and essentially highlights the searching area. Now, how does the BFS work? The BFS work is the heart of the scratch. From each point, we explore 3 neighbors. We explore right, up, and diagonal, and we expand in concentric layers, tracking the visited points to avoid redundant work. So how it works is it takes an invisible point, it goes up, it goes towards its right, and it goes diagonally up and check if all the 3 points that in consideration are invisible or not. If either of them turn out to be visible, it moves on to the next iteration. And if all 4 of them turn out to be invisible, then it terminates the program and gives us the coordinates of the point where we can find a 2 cross 2 block. So we ran this search for the given families, A comma B, in a 1000 cross 1000 lattice. And these were the results that we found. We found that for 1 comma 1, the point that we found was 13 comma 195. For 3x squared plus 2x, we found 25 comma 12. Now, some patterns that we also found. The coordinate 13 comma 195, it was recurring around multiple different A comma B pairs, suggesting some shared underlying structure in the lattice. Secondly, the polynomials with larger coefficients tended to show no invisible block within our bounds. For example, 4x squared plus 9x, we could not find any 2 cross 2 invisible blocks. Of course, our search is limited by computational capacity. We did not have access to GPUs, so this is the maximum that we could get. Finally, I would like to summarize what we did. We first generalized visibility from linear and monomial curves to higher degree polynomial curves through GCD conditions. Along the way, we established results, density estimates, and some constructive examples of both visible and invisible points. And then our computational experiments yield these results, which also leaves room for deeper arithmetic patterns, which are hidden in polynomial groups, which are yet to be seen. Now, there are 2 directions which evidently came into picture. The first is developing a notion for two-way visibility. The conditions that we have were single implications, and we did not find any double implication condition, which is why the study of lattice points in polynomial lattices still has some scope. And and the second is that we generalized our 2 cross 2 block findings to full entros and patterns so that we can understand the structure, the density, and the locations. Thank you, and I'm happy to take questions now.
Oh, thank you very much. Are there any questions for our speaker? If not, we thank Chahat again, and our next talk will be in about 10 minutes.
Thank you, sir.